Well, good morning, good afternoon, good evening, whatever time it is for you. My name is Benjamin Lehmann, and I'm a PhD student working with Stefano Profumo at UC Santa Cruz. If after you watch this video, you want to chat about any questions or ideas outside the allocated discussion time, feel free to send me an email. My address is right here next to my name. As the title says, I'm going to tell you about how we might soon detect new forces in the gravitational wave background. Let me linger for just a moment on the title slide so you can enjoy this lovely picture. It might look like kind of a Rorschach test, but it's really meant to show two merging black holes, and that's going to be the focus of this talk. So let me actually begin here on this plot of the anticipated astrophysical sources of gravitational waves across the spectrum. There's a lot of good stuff to the right and the middle. I just want you to focus on the leftmost part of the plot, where the label says stochastic background. So here the actual sources are the heaviest binaries composed of supermassive black holes, somewhere around 10 to the 9 solar masses. And in this nanohertz regime, we do have an observational handle on the gravitational wave background in the form of pulsar timing arrays. So this is exactly what nanograv, for example, was set up to detect. Now here's the question I want to pose. Suppose that pulsar timing arrays see gravitational waves from supermassive black hole mergers, or maybe they already have, right? If those gravitational waves really are just from black holes and not from any exotic sources, then how can we use them to probe fundamental physics nonetheless? So with that as motivation, let me start right away with the takeaways because my attention span is frankly not what it used to be. So here's what I'm going to explain in the rest of the talk. First, gravitational waves from supermassive black holes are an imminent guaranteed discovery. Whether we see it or we don't, we're going to learn something interesting really in the next few years. Second, I'm going to show you that new long-range forces can change the spectrum of this gravitational wave background in ways that are robustly detectable. And third, through this gravitational wave background, supermassive black holes become a very powerful laboratory to probe lots of new physics on otherwise inaccessible scales. So to explain how this works, I first want to remind you how we go from talking about binaries to talking about a stochastic gravitational wave background. The picture here is that galaxies typically host supermassive black holes at their centers, and these galaxies are merging over cosmic time as structure forms hierarchically. So that means that there's a sizable population of supermassive black hole binaries that are merging over cosmic time. In fact, I can show you an actual picture of a galaxy with two supermassive black holes at the center. So as these supermassive binaries are orbiting, they radiate a ton of gravitational radiation for a timescale of years. So instead of looking for individual mergers like we do at LIGO, it makes sense to look for the incoherent superposition of these gravitational waves that are emitted over cosmic time by many binaries. And that's the stochastic gravitational wave background from these compact objects. So this stochastic background is expected to be detectable by pulsar timing arrays. If not now, then very soon. So what do we actually expect to see? Well, this is a prediction of the stochastic background spectrum taken directly from the astronomy literature. Up to some cosmological factors, this is effectively just adding up the spectra of individual binaries. The horizontal axis here is the frequency, the vertical axis is the characteristic strain, the amplitude of the background, and the spectrum here is a nice power law, right? It's got this index of -2/3. I want to emphasize this point. Even though the amplitude of this line is quite uncertain, you have these wide bands for different classes of models, this f to the -2/3 behavior is pretty robust. The uncertainty lies mostly in the distribution of sources, right? But each source has the same f to the -2/3 spectrum. So the shape is the same almost no matter what. Now, what I'm going to show you is that new forces can actually change this robust f to the -2/3 power law. But in order to do that, let me first explain where this -2/3 index comes from in the first place. And that comes down to the relationship between the emitted gravitational waves and the evolution of the binary. So towards the end of the merger, gravitational waves are the primary mechanism driving the binary to merge. So in turn, that means that the observed gravitational wave emissions are directly related to the evolution of the binary. Let me make this concrete. Here's the spectrum of gravitational waves that are emitted by a single binary. And the main non-trivial ingredient here is this derivative in red that contains the relationship between the binary separation and the frequency of the gravitational radiation that's being emitted. For circular binaries, this is really easy to work out because the gravitational wave frequency is just twice the orbital frequency. So really all you have to do is work out the relationship between the binary separation and its orbital frequency. That's just Kepler's third law. So now if you turn the crank, you will find that the strain spectrum goes like f to the minus 2/3 as promised, but this all relies on gravity being the only mechanism at play. If you have another significant driver of the merger, then you can break this connection between the gravitational waves and the evolution of the binary, and that changes the shape of the spectrum. So just to recap, there are two assumptions that determine the power law spectrum. First, there's the relationship between the frequency of the gravitational radiation and the orbital separation of the binary. For gravity, that's just Kepler's law. And second, one assumes that gravity dominates the evolution of the binary, right? In the sense the binary is only losing energy to gravitational waves and nothing else. So if either of these assumptions is violated, then you can have deviations from the simple f to the minus 2/3 spectrum. And in principle, you could think of lots of new physics scenarios that could show up this way. So as a benchmark, as a toy model, we're going to imagine that the black holes are subject to some new, beyond standard model, long-range force. And maybe the simplest conceptual picture here is that the black holes carry charge under that new force. That's certainly not the only possibility. I mean, you could just as well imagine that the surroundings of these black holes are charged. All we care about for the purposes of this toy model is that we have a charge distribution which is point-like compared to the separation of the binary, like the picture. So this long-range force is going to have two effects. First, because gravity is no longer the only force, the relationship between force and distance, the binary separation, gets changed. And that means that Kepler's law is modified. So in particular, the connection between the binary separation and the orbital frequency is now different from the gravity-only case. And second, the binary can lose additional energy to radiation of the mediator of the new force. And because there are these two effects, I'm going to talk about the charges in terms of two parameters, alpha and gamma here. Each parameter controls one of these effects, violating one of the assumptions I talked about earlier. So alpha is proportional to the product of the two charges. It controls the force between the black holes. If you like, that's the modification of Kepler's law. Gamma contains the charge difference between the black holes. So that controls the dipole moment, and that controls radiation of the new mediator. So again, alpha changes Kepler's law, gamma controls non-gravitational radiation. If either of these parameters is non-zero, then modifications to the dynamics of the binary give rise to new features in the gravitational wave spectrum. So with that, it's worth spending a few words on what kind of physics might actually give rise to new charges in the vicinity of black holes. And this is a pretty rich subject. There are some ideas out there in the literature already. There are some that we're just thinking through now. But to give you a taste of what the supermassive black hole environment can do for us as physicists, let me list a few possibilities. So first of all, the environment around a supermassive black hole is a great place for new particle physics processes to happen. So if you have highly energetic baryons nearby, as most of these black holes do at some point, then it's possible to produce new beyond standard model particles that could carry these new charges. Second, beyond the baryons, these black holes are in dark matter dense environments. So if dark matter carries small charges that can accumulate into a tight clump near the black hole or even get accreted. Third, even if you have a net neutral charge, it's possible that positive and negative charges could be separated if you have large magnetic fields or a dark equivalent. So that charge separation can give you a large dipole moment or a large gamma in the language that I was using before. One more, fourth, if there are light bosons in the spectrum, then they could be produced at some point by superradiance. So there are potentially many more of these mechanisms. I just want to make the point that there's a lot of rich physics related to supermassive black holes and their environments, and that's what we can potentially probe in this way. And at this point, for those of you who are mainly excited about the stochastic background as a probe of the black holes themselves or other cosmological significance, I also want to just take a moment to highlight the significance of discovering such a new force. See, I say new force and I get very excited, but I want to connect the dots here. Any such discovery would be the first step towards uncovering new degrees of freedom and potentially resolving some of the deep open problems in fundamental physics. So there are really very compelling reasons to look for such long-range forces. And the idea that pulsar timing arrays could actually detect such a thing in the very near future is quite exciting. Now, for the moment, I'm not going to insist on any particular mechanism or particle physics model. I'm just going to parameterize the charge with alpha and gamma, those two parameters. And I'm going to assume that the charge distribution is point-like relative to the binary separation. Now I want to get on with business and show you what actually happens in the gravitational wave spectrum in the presence of such a new force. So let's see how alpha and gamma modify the spectrum of the gravitational wave background. Here again is the gravitational wave spectrum, but with one modification at the right. Remember, the form of this spectrum comes from the relationship between the energy lost to gravitational waves, but now that's only some fraction of the total energy lost. So that's being captured here by this factor on the right, and I'll write that out for you in more detail in just a moment. But there's one other difference between this relationship and the usual gravity-only case, and that's contained in this derivative. So remember, that derivative contains the relationship between the binary separation and the orbital frequency. So in the presence of a new force, that relationship is modified. And we're parameterizing the new force in this way here, assuming that it has some mediator that has a non-zero mass, little m. In that case, the force has a finite range. So there's an exponential cutoff when the separation of the binary exceeds the range of the force. Now, as advertised, we have two effects. This second one is obviously controlled by alpha, that determines the strength of the new force. You might have guessed that the other one, the radiation, is controlled by gamma. And indeed, if we write out the power emitted in radiation of the new mediator, it's proportional to gamma squared. Let me also point out that there is a threshold effect here. The real part of this red piece is only non-zero when omega is greater than m. Or in other words, the radiation turns on when the orbital frequency of the binary exceeds the mediator mass. Now let me show you what the spectrum actually looks like for non-zero alpha and gamma. And let's start with alpha greater than 0. So again, here, that means that we're changing Kepler's law. This plot is showing the spectrum for a single source in ratio to the gravity-only case. Okay, so the gravity-only case is the black line. Each of the other lines shows a non-zero value of alpha, and the outermost line over here corresponds to what happens when the black holes are nearly extremal. Now, something really important to understand here is that the lowest frequencies on this plot are emitted at the largest separations in the binary's evolution. Okay, so if the force has a limited range, then it's ineffective at the lowest frequencies. But as the binary shrinks, eventually the new force does turn on. And that's why there's a kink at this location in the spectrum. That's fixed by the range of the force, or equivalently by the mass of the mediator. In any case, the interesting thing is that, as I promised, there is a bend in the spectrum compared to the gravity-only case. So this is not going to be an f to the minus 2/3 power law. We can do something similar for the gamma parameter. And remember, that controls additional dipole radiation. Here again is the single source spectrum, again in ratio to the gravity-only case. And once again, there is an obvious effect on the power law index of the spectrum. And notice I'm now showing curves for a massless mediator. So here, for an infinitely long-ranged force, there is still a clear change in the power law of the spectrum. If we do have a finite range force, then we get an interesting sharp feature. You get this dramatic step in the spectrum when dipole radiation turns on. So for non-zero gamma, you can see a massless mediator, or you can detect the threshold itself if you're lucky. So there are these unique features in the spectrum. Now, everything that I've shown you so far is for a single source, right? A single binary. And really, to compute the observable strain amplitude, one has to take that single source spectrum and convolve it with the source distribution of the binaries. And here, at least, we don't have to invent anything new. We do this exactly as it's usually done in the literature for gravity-only mergers. And that brings you to plots like these. When you add up all of the sources over cosmic time and compute the strain spectrum, the actual observable, you get results like these. So in each of these panels, the black line is the gravity-only case. But in the left panel, we have non-zero alpha, meaning that we're modifying the force law. And in the right panel, we have non-zero gamma, meaning that we have additional dipole radiation. The main thing that I want you to take from this is that all the features we just talked about at the level of single sources survive to the actual observable. The features get smoothed out a little bit by redshift, but the modified shape is clearly observable both at the level of the power law index and at the level of local features. So for example, here's that dipole radiation threshold. The gray region on these plots is the projected sensitivity of pulsar timing arrays. And this is a point that sometimes takes people by surprise. So let me emphasize this. Pulsar timing arrays seeing supermassive black hole binaries is really a when and not an if, and it's coming up now. Okay, pulsar timing arrays are already sensitive to the most optimistic astrophysical projections. And even in the most pessimistic scenarios, we should be seeing something on the timescale of years from now. If we don't see this background soon, that itself points to something interesting. That said, depending on whom you ask, pulsar timing arrays may already be seeing their first hints of a stochastic background. So now let's talk about the prospective signal from nanograv. The nanograv signal could be a whole lot of interesting things. It might not even be gravitational waves, but it could also be the first hints of a stochastic background from supermassive black hole binaries. It's just too early to say exactly what we're seeing. That said, it may be too early, but it's extremely fun. So let me show you anyway what happens if we interpret the nanograv signal in light of our toy model. This is the nanograv result as a fit in the plane of power law index and amplitude. So taking this plot at face value, we can already begin to constrain certain values of gamma for a massless mediator. And I should say, it's still non-trivial to interpret this as a measurement of the spectral index because of how early on we are in observing the spectrum. So depending on how you do the measurement, it's actually possible to get a preferred region towards the right-hand side of this plot, which would be very interesting. But there's no need to speculate. The dataset is growing very quickly, so we'll be able to probe this scenario very concretely very soon. So this is just a teaser. Now, I want to say a few words about where we're headed next. What we showed in this paper is that new long-range forces can change the dynamics of supermassive black hole mergers, and that can give you observable features in the spectrum. But really, any new physics that changes the dynamics can do the same thing. And there are some really interesting possibilities that we're looking into right now. So for example, even if you don't have a point-like charge distribution around or on the black holes, you could very well have diffuse clouds of charged particles, which could have their own effects on the dynamics. You could potentially see a dynamical effect from dark matter in particular scenarios. If you have some non-minimal dark matter microphysics and you have a dense spike near the black holes, that potentially modifies the dynamics as well. I'm going to list superradiance one more time. I mentioned it before as a mechanism for producing particles, but in principle, superradiance can also remove angular momentum from a binary and have its own dynamical effect. So there are lots of interesting possibilities. We're just studying these now. What we've done here is really the first step. Okay, let me wrap up. To recap, we can expect a guaranteed discovery of this stochastic background or its absence in the coming years, with significant implications either way. And we showed that a new long-range force can make observable modifications to this background. So we've taken a first step towards using the background as a probe of fundamental physics. I say a first step. The case of a new long-range force demonstrates the phenomenology nicely, but it's really just the beginning of the story. What we've shown here is that any new physics with implications for the dynamics of the binary is potentially detectable with unique spectral features in the gravitational wave background. And we're working now on developing exactly the same methodology to study other new physics scenarios. And there's some very interesting possibilities. So I want to leave you with the idea that supermassive black holes are, of course, very powerful laboratories for new physics. But more than that, we now have an observational tool for actually reading out the results of these kinds of experiments in the sky. So I look forward very much to telling you what we learned from this with new data in just a few years.